Our derivation of the worst case big O time complexity for finding an element in a red-black tree assumed that we have a valid red-black tree. So for a red-black tree to be valid, there are a few different properties that must be maintained. If we talk about the insertion algorithm into a red-black tree, we can't just do the simple binary search tree insertion because that might break those properties of a red-black tree. So we have to be a little bit more sophisticated to ensure that our red-black tree properties are maintained even after our insertion. So to show you the insertion algorithm, we're going to break it down into the different possible cases or scenarios that you might face. So the first case is the following. What happens if we're inserting an element into an empty tree? This is the most trivial case, and all we have to do is insert the new node as the root of the tree and then color it black. So let's say I insert the number 20 into a red-black tree. It's empty, and now I create a new node that is the root, and it's black. Before we introduce the non-trivial insertion cases, the insertion cases that happen when the tree is not empty, I'll first give you some guidelines that have to occur in all of the upcoming insertion cases. So in general, if you have an insertion case where your tree is not empty, you first perform the regular binary search tree insertion algorithm. As you're doing your tree traversal down the tree, if you ever see a black node that has two red children, so in other words, if you ever see this scenario, so a black node that has two red children, recolor all three of them. So in other words, you would recolor them such that the parent is red and the children are black. And then, by the way, if the parent happens to be the root of the tree, remember that in a red-black tree, the root must be black. So if you do this recoloring, but this is actually the root, just recolor this to blue again. To black again. Okay, so that's while you're doing your traversal. Now that you found your site of insertion, color the new node red when you've inserted it. So these two things will always happen in a red-black tree, in all of the cases. And then, depending on what happened, you might potentially have to fix your tree to maintain the red-black tree properties. So this is really where the different cases will come into play. How exactly we may have to fix the tree to be able to maintain the red-black tree properties. So the first non-trivial case that we'll face, which I'll call case 2, is when the new node that you're about to insert is going to be the child of a black node. So let's say I'm inserting a new node, and I'm doing the insertion, I'm doing my binary search tree insertion algorithm, and I hit V. V is just some node, and I see that, oh, my new node needs to be the left child of V. My new node, which I'll denote as X. So these are not alphabetical order. I'm just using variables to denote the different nodes. So let's say node X is my new node, and it becomes the left child of V arbitrarily. Remember, new nodes get inserted as red nodes, so I just followed the instructions as I was expecting. It turns out that if your new node is the child of a black node, you're done. That's all you have to do. You have not changed the number of black nodes along any given path, so everything is totally good. Similarly, so in this example, I had X end up being the left child of V, but what if it ended up being the right child of V? So let me make another node Y, that's the right child of V. Again, I'm not using alphabetical values, these are just variables. Again, no need to worry about it. If the new node that I've inserted, which must be red as per my rules of general insertion, when I insert it, if it ends up the child of a black node, I'm done. Let's take a look at the next insertion case. This is when the new node is the child of a red node, and it forms a straight line between its parent and its grandparent. And specifically, how we would fix this is, well, we would first do the insertion as normal, then we would do a single rotation, and then we would recolor. So what does that mean? Okay, so let's say I have this example, and let's say my new node x, again, remember these are just variable names, they're not alphabetical order. I insert a new node, variable name is x, it becomes the right child of v. Now I have a red node with a red child. Uh-oh, that's not allowed. So what I can do is a left AVL rotation on my new node's parent and grandparent to rotate them counterclockwise. The result would be, and then this question mark is just some other part of the tree. I have all that stuff remains unchanged. Then V is now over there. And then W becomes the left child of V. And then X remains unchanged. Draw my edges. And then now I can recolor. So this was the left rotation. Now I can recolor those nodes to fix my binary search, my red-black tree properties. So again, this is what's happening elsewhere in the tree. Now I have V is a blue node, and now W and X are both red nodes. So now I've fixed my binary search tree properties. And similarly, let's say I had this directional line. So let's say I insert a new node X and it ends up over here. Oh, that's not color consistent. I've been using purple. There we go. Let's say I inserted a new node that becomes the left child of V. Again, I have a straight line between my new node, its parent, and its grandparent, and I'm not allowed to have a red node with a red child. So I do an AVL rotation on my grandparent and parent. This time I'll do a right rotation. So I'll draw this over here. Some tree stuff over there. So now I have V as the parent. X remains its child. W is now its child. Whoops, I used pink again. I've been using purple for the edges. And then now I recolor. So I recolor, whoops, I recolor these two nodes. And now I get whatever was going on in the tree. I'm just going to draw my edges so I don't forget. Then I get V is now a black node, and X and W are both red nodes. So it's the exact same scenario as this scenario, except instead of doing a left rotation, I do a right rotation. So now that I've done this scenario is fine, and this scenario is also fine. Now for our last insertion case, when our new node becomes the child of a red node, but this time we have a kink shape. And to fix this, we would first rotate to make a straight line out of our kink, and then we would just do the straight line insertion case from there. So let's take a look at this example. Let's say I have this tree here, so I have some amount of the tree over here, then I have a grandparent, W, that's black node, and again, remember these are variables. Then this is the parent, and my insertion site of my new node X happens to be here as the right child of V. Now I have a kink shape. So I have a red node with a red child. I'm not allowed to have that. But I have this kink shape here between my new node, its parent, and its grandparent. So to fix this, first I do an AVL rotation on my new node and its parent. So this time I would do a left AVL rotation to rotate counterclockwise. let's see what would happen. We would get, so this stuff up here remains unchanged. W is still its right child, but now we have X and V. Let me draw my edges. Now we have X and V in a straight line. So now these three are in a straight line. Do the straight line fix. We know how to fix this. We've already covered it. So now that we've got it into a form that we can fix, just do the fix, which remember it was AVL rotate right here and then recolor. Similarly, let's look at the mirrored example. Let's say I insert my new node X. Again, these are variables, not alphabetical values. And X becomes the left child of V. So again, I have a red node with a red child, not allowed to do that. And again, I have a kink shape between my new node, its parent, and its grandparent. So first, I will do a right AVL rotation on my new node and its parent. Let's take a look at that. So here's the rest of my tree. Then W remains unchanged. Now X is the right child of W, and V is the right child of X. Draw my edges. So after I've done this rotation, now I'm left with the straight line example that I've seen before. I can fix this easily. So again, do the straight line fix now that I have it. So remember, I would do a left AVL rotation on the parent and the grandparent. And then I would recolor. So now we've covered all theoretically possible scenarios in which we could insert a new node, and we've found out how exactly we can fix our red-black tree to maintain the red-black tree properties.